Our next speaker is Alexey Rybakov from LUXOFT. His talk is on making computer vision software run fast on your embedded platform. He's a senior director at LUXOFT, manages their embedded systems practice, and provides embedded software consulting, research, and engineering. He's got a software engineering background, and he's held a variety of positions in the embedded software industry. Alexey?
So, friends, thank you for gathering here for our optimization, software optimization presentation. First, I need to tell you why LUXOFT is giving this talk. Although we are a large, publicly traded company, and we not all of our work is in software optimization, especially in embedded, but actually we have a pretty large team, roughly 150 people, that was working for many years in optimizing vision, video, and imaging software to run on non-desktop, non-PC platforms. And this talk is actually considered a summary of our experience and things that we learned during all these years. And we developed a certain, it's probably not a methodology, but a set of rules, what we follow in our team in order to implement optimizations. And these are, on the screen, you can see projects that will be highlighted briefly on this talk, because it's almost impossible to cover years of software optimization in a 20-minute presentation. First, quick qualifying question. Who develops software versus hardware? So who is in the audience who's dealing with the software? All right, it's good already. Although we cover software implementations as well, this talk, for simplicity and introduction purposes, will rather be focused on porting, optimization, acceleration tasks, because too often we have our classic desktop or cloud implementations of algorithms available, because computer vision is a field with at least 30 years of history. So we have many classic implementation of the algorithm, and often our task is just to make it run on embedded software. What I'm going to talk about in this talk is actually we have about 6 approaches that we rather would take in the order that's listed on the slide. I will talk about the platforms and how to map algorithms work on different compute cores and compute engines that are typically available. Then we'll talk about reworking both the requirements to the embedded algorithm compared to classic algorithms, and reworking its logic based on that requirements. Also, most of mobile platforms have very powerful non-CPU architectures that we need to consider. And lastly, we'll talk a little about how optimize already on a code level and on a platform-specific level. All right, our first subject is mapping computer vision pipeline into our platform. So in this slide, you see a typical a diagram of embedded systems, of embedded computer vision hardware. So what it actually does, what's the entire task of the computer vision? So we take the real world scene and we derive decisions and metadata based using all these compute cores. So, and because this is a non-PC architecture, we often what we see in our practice is that software engineers just port their algorithms straight and turn off GPUs or DSPs because algorithms initially was not designed to take advantage of these compute cores. One thing that we need to, the first step that we always do with when we take the task to port or optimize an algorithm for embedded platform, we always study and evaluate the platform and just don't assume. Benchmark everything, because in almost every case, we see a lot of surprises about how platform actually behaves compared to either previously known platform or compared to the documentation or, of course, compared to the desktop implementation. So benchmark everything, compare to performance of the same operations, especially its memory transfers, because typical embedded platform would have more types of memory and more heterogeneous compute cores. So benchmark this, benchmark your compute performance, and this will give you numbers that you need to stick to when you do your optimization project. Just a little example. One of our customers was porting an algorithm, and we will use the histogram algorithm pretty often in this talk, because this is very simple and very easy to understand, onto GPU-enabled platform. So here you can see that there are option A on top as a CPU implementation, option B on top of a histogram collection. Although the algorithm itself on the CPU is not as efficient. You can see on yellow bulb there, the first thing that we do, we measure memory transfer performance. And we find that memory transfer is not very efficient in one way. That's why even by reducing the calculation time, we don't gain in the actual algorithm performance. So, and these are tasks that and approaches that we typically do. So we measure everything and we put our modules of our algorithms onto different compute cores based on memory transfer and computation performance of the system in general. And take the whole system, as it's not just component-based. Second thing is system requirements. So basically, to emphasize it, to express it in one sentence, if your computer vision system needs to only recognize triangles, strip down everything else, just throw it away, and make it only leave there only functions that are responsible for recognizing triangles. That's the bottom line. Because universal algorithms are too power inefficient, too memory inefficient, and they do a lot of assumptions that you actually need or you already know about. Quick example. In one of our projects, we are taking pretty new work of MIT and Google in obstruction removal. And our task was to make the drone implementation of it. So universal implementation, it can take any motions, opaque or translucent, obstacles, and so on. So in our task, we don't need it. We only take linear motion because drones fly most of the time in one direction. Also, if they don't, we have gyroscope data available to throw away these frames. And we need to care about wires, tree branches, and so on that are always opaque. Just by making these simple assumptions, performance is more than 100x improved. And in many algorithms and many porting problems, it's the same approach. Excuse me. Connected subject to it is algorithm logics. And here on this slide, there are typical opportunities for working with algorithm logic. Just take it by example. Automotive cameras are often already high resolution. Those who've been on in the cafe tutorial yesterday, we understand how much computational power we need to effectively do the pedestrian recognition, for instance. Okay, let's count. Downsampling. If you reduce HD resolution at least twice, 4 times performance. You strip down the color, 12x. Instead of the entire frame that you put through DNN cruncher. You first execute very power efficient and very fast histogram of gradients that will give you only regions of interest that you will put into your neural network. And these regions of interest would typically cover like 10% of the entire frame. So this is 12 by 10, 120x the performance. Now we don't have to do this on every frame because pedestrian who is there on one frame will not disappear on the next. So we would typically use, again, very cheap tracking algorithm for that. And only run detection on every 10th frame, which gives us more than 1,000x, only by simply following the steps and reworking algorithms in this simple way. One more example is classic video stabilization algorithms. They used to run as a offline post-processing algorithms because they used to take every pixel or 8x8 areas and so on. For most of the consumer shooting, we actually derived that it's sufficient to only take 9 vectors, and it's already enough to make pretty high quality consumer motion stabilization. We do some other tricks, but generally it's, again, more than 1,000 times the performance. One more important subject to cover is that non-CPU architectures that are currently dominating or in some areas beginning to dominate the embedded world. There are some basic recommendations. Paradigm of programming is different. You need to care about memory, alignment. You need to care about types, because as you benchmark, you will learn that these types, they behave very differently in these platforms. Just for introduction, this GPU subject is most of our projects we deal with GPU and OpenCL. So it's like at least 3 days of full-time sessions. But just for one slide, classic example, matrix transform. You have 100 GPU cores. So you divide your matrix into 100 little tiles, and you run each core to transpose one tile. This is what you do. So, this is the example of parallelization. So here you both load 100 cores independently. Also, because each core is tiny, each matrix segment is tiny, it fits into local memory or private memory, and that's why you have very efficient operation that like 1,000 times faster. And things like that, you can see at our booth. We did that same thing for accelerating Café on ARM Mali, for example. So to keep long story short, we did a lot of things, but one significant major one was that we not only ported that to a better OpenCL framework that was initially designed for, we also profiled and benchmarked every major block there. And we found that matrix multiply was done in a completely inefficient way there initially. So we rewrote the as GMM functions. We get at least 8x in performance. And now we have neural network running live on Samsung with 5-6 FPS. And as I mentioned a couple of times, it's important to benchmark everything. And this is the example of how we do it. We just don't measure one time. We measure it for long continuous time because we know that mobile platforms, they also have power management mechanisms, and they also kick in. So as you can see in a CPU graph, performance actually degrades only because power management. And there are many examples like that. So just, again, you cannot underestimate benchmarking and measuring. One other large project that we did, and it's available on various GPU architectures and frameworks, including NVIDIA, AMD, Intel, is a VP9 decoder. And again, this is an example of efficiently using GPU to enable YouTube playback on various home media centers. And without proper use of GPU, it would be impossible because the difference is 10 frames per second versus 60 frames per second. It's completely different viewing experience. So now as we're done with this subject of using GPU, we'll talk a little about the code optimization that we also do in almost every project. So it's hard to give a lot of guidelines here, but the concepts are pretty simple. Don't calculate and don't move data. So use lookup tables. Also, as we've seen in cafe and deep learning examples, for instance, you just don't use sigmoid, you use linear, and from like 75% accuracy, you get 76% accuracy in the end, but you get 10 times the performance. There are many examples like that. Now another example that of that same thing, of code optimization, we benchmarked everything, the GPU performance for one of the open CV algorithms. We played with many different implementations. We benchmarked that. And by using one of the methods, it's incrementing in global memory, we now have under 1 millisecond, which gives plenty of budgets for full frame 60 FPS processing on HD, for instance, which was not possible in the initial implementation. Couple of other tricks. You see table on the right. You would typically need this for your platform. It's different for every platform. You just better have this. You need to understand the cost of your operations. Memory transfers are almost always pretty expensive, especially if it's global memory or off-chip memory. That's why even if you have to calculate the same thing 10 times in different places, often do this because moving data is way more expensive. And finally, just know your platform inside out because all platforms are different. And not only that, different versions and subsequent editions of CPU cores, compilers, tool sets are very different from one another in terms of performance and how they implement low-level functions. So couple of examples here. Task of frame rate conversion. It appeared that, for instance, many platforms don't do this, but one specific platform does. It's one instruction upscaling of motion vector field. And again, this is very platform specific, but for your given task, if you read carefully the optimization guide for your platform, you will find probably just some magic function that will work for you. Another example, even even on Apple iOS, it's possible to do a low-level optimization. But again, don't trust everything you read in the documentation, because often things just don't work, or they don't work as documented. But with workarounds, it's possible again. So just to reiterate what we learned here, it's very important to test, benchmark, and profile your system entirely. Don't port one-to-one. Rethink requirements, rework algorithm. Use GPU, DSP, FPGA, other compute engines. They may give really great results for you. It's mix of art and science. So there is no ready recipe. Just try to read and experiment as much as possible, and you will get great results. And for details of the projects that were showcased here, you're welcome to visit our booth and talk with our team. A couple of resources, actually initially was like 50 different links. That's why I better send your documents by email. And I would like to thank you, LUXOFT team. It's roughly 20 people who actually was working on preparing this material. This is a part of our team that's doing this projects for a year. So thank you very much. I'm based in Menlo Park, so those of you who are local also welcome to visit us for a cup of tea. Now, Vince, that little administrative announcement. Some of you may have these pink tickets. So I get an advice from organizers that the way better venue for Apple Watch draw will be during reception at about 5:30. So visit our booth for tickets, and LUXOFT will give away one Apple Watch for attendee of the Embedded Vision Summit. Thank you very much.
So I have an Apple Watch, so I'm not eligible for the drawing, but I highly recommend it if you're so inclined. It sounds like you've got a lot of experience putting these embedded platforms together, and I would imagine that at least for the audience, there might be some bruises on your knuckles or on your knees or someplace having used specific platforms. So you didn't really talk about trying to favor one type of platform over another. Do you have any advice for the audience about the selection of the hardware, or is it one of those things where?
I do. Yes,
okay.
I do. So if you're lucky enough to know your algorithm and your task before you get your device from your hardware lab, you're really lucky. This is the thing. This is the way to do things properly. So the advice is very simple. So you study your algorithm. You understand what are critical components of it. You benchmark it on a desktop platform, or on some a couple of developer kits that you may purchase on DigiKey or where have you. And then based on that, all tasks are very different. Okay. That's why DSP may work better for one. Some custom FPGA, if you have budgets for that, may work for another task, or GPU for the other task. So advice is to first learn your system and then make decision if you can.
So do the analysis before you do the implementation.
Exactly,
okay,
yeah.
Great. I think that's great advice. Other questions? We have some mics. Let's bring the mic up here. We have plenty of time, by the way, so we're running a little ahead of schedule.
Thanks. Charles Xu from Cadence Design. So I have a question for you. When you do the benchmarking of the platforms, particularly when you try to utilize the GPU or DSP resources, how often do you rely on vendor-provided optimized libraries versus doing your own exploration of programming in intrinsics or
Yeah, so thank you.
threading,
it's a great question, and actually I had discovered in the slide, we just didn't have time to talk about it in this detail, that hardware is not the only component or foundation for the algorithm. We also have libraries, we have compilers, we have tool sets, and so on. So sometimes we gain a lot of performance by changing the tool, changing the algorithm, or using a different version of compiler, for instance. That's why, no, we don't always rely on only vendor provided tools and vendor provided frameworks. And as you can see in a number of examples, we either have to benchmark something manually, or even if vendor has provided a software framework like OpenCL, for instance, we rewrite parts of it that are critical for our specific task. Any other specific? Okay.
I got a question here that no engineer ever likes to answer. How is it that you estimate schedule for how long it's going to take for an optimization task?
It's almost, as I said, it's a mix of art and science. That's why it's half my experience of doing similar projects. And half we parallelize internally. So we have a luxury of having a team that's doing this, which constitutes of more than 150 people. So internally we are lucky of having some resource flexibility here. But it's experience, and well, optimization can take forever. So you measure, benchmark your system. You know the numbers, like you have to optimize it 50 times, and then typically in the first quarter of the project, 25% of effort should give you at least half of the result. If you don't get half of the result, you're probably in trouble.
Fair enough, thank you.
Good rule of thumb. Yep.
Would you still do today with all the libraries available? Now it's working. Do you think today is worth the effort to do really kind of deep level assembly optimization, or is it enough to just take the library as it is and take some optimized library? What do you think to get really to an optimized solution?
So we have more than a dozen platforms available, or more than 100. And more than 10 different frameworks. It gives you a combination of at least 1,000. So don't expect that every framework will be already optimized for the platform you're going to use, especially with the pace of progress today. So that's why we always optimize frameworks. So we rewrite OpenCL, we rewrite OpenCV, and yeah, at times we use inline assembly, but more often it's high-efficient C code. Did I answer your question? Thank you.
All right. Thank you. Any more questions? We got time for one more. Okay, great. Well, thank you, Alexey.
Thank you, Vincent. My
Appreciate it.
pleasure.